So, Dr. G, is it true that the two-group model always explains more variation than the empty model does?
Good question. So we want to answer this question simply, and that's yes, that's always true. But the question is why? Why does it explain more error, more variation than the empty model? And so I kind of want to delve into that. And the real trick behind it is that the leftover sum of squares, so the sum of squares total from the empty model, is always going to be bigger than the leftover sum of squares from the model, right? Which we call sum of squares error. So I just want us to keep that in mind here. So the sum of squares total is always going to be bigger than the sum of squares error, right? And so this is from the empty model, and this is from the two-group model, right? So this is the real reason why, right? So why is this true? Well, that's because one mean is worse than two means, and that's really the key. So sum of squares total, that's minimized by one mean. But sum of squares error from the two-group model, that's minimized from two means, and two means explains more than one mean. Right? And so that's really what we're going to focus on today. Why is two means better than one mean? Why is there less error from two means than there is from one mean? So let's go back to tiny fingers, right? Our favorite data set, right? Here are these thumb lengths of 6 people. And here we've shown it to you in this point plot. And you could see that there's variation here. And we've also put in the empty model, which is just the mean. Here, you could see a residual from the empty model. And sum of squares is you take those residuals, square them, add all of them up. That's the sum of squares total, right? But imagine that those 6 thumb lengths actually came from 2 groups, right? And we actually just randomly put them into groups. So they're not special, but we just put them into 2 groups. And we've colored the dots. There's the red team and the blue team. So now that you see them in 2 groups, has the sum of squares total changed at all? No, right? Just because they're different colors, just because they belong to different groups, doesn't mean sum of squares total has changed at all, right? But just visually, we're going to separate them. So now we've separated them. But again, let me ask you, has sum of squares total changed? No, right? Because the residuals are all the same. We've just separated these points out. But the residuals from the empty model are all exactly the same. And when we square them and add them all up, it's going to be the same, right? So sum of squares total has not changed. Let's put in the complex model based on these 2 random groups. The group model. Ta-da! So here we have the 2-group model, right? So here's the group mean for this red group, and here's the group mean for this blue group, right? And now we could see there's error from the empty model, but there's also now error left over from the 2-group model, right? And so let's illustrate that with just one of these dots right here. So let's pick this point right here. This person has a thumb length of 66 millimeters, but the empty model would have predicted that they had a thumb length of 62 millimeters. And so here is the residual. I'm just going to draw it off to the side just so that you could see it. Here is the residual from the empty model, right? That's how long it is, right? And I could have drawn it right underneath, but I just didn't want it to get in the way of the other points, right? So now let's look at, well, what would the group model have predicted for that person? Well, the group model would have predicted this line right here, which is 63 millimeters, right? And so the error from that model, I'm going to draw right here, looks something like that, right? And so the sum of squares total is made up of these lines, right? These lines, when we square them and add them up, makes up sum of squares total. But the sum of squares error is made up of these lines after we square them and sum them up. So let's get back to our question. Why is the sum of squares total from the empty model, why is that always bigger than the sum of squares error from the 2-group model, right? Okay, so let's take these points and let's consider, well, what if we just took this group and we ignored the fact that we actually could calculate its group mean and said, you know what, I just want to use my empty model right there, right? And I'm going to also take my other group and say, I don't care that I could use the group mean. I'm going to just use the empty model. Right? Now here's the trick. Remember a long time ago we said to you, the sum of squares is always minimized from that group's mean? Well, notice that is not the mean of this little group of numbers. And that is also not the mean of this group of numbers. So this sum of squares is going to be bigger than this group's sum of squares. Why? Solely by the virtue of the fact that this sum of squares really is being calculated from that group's mean. So if this one is bigger than that one, and this one is bigger than that one, and sum of squares is when we add those two together, it stands to reason that this whole sum of squares is going to be bigger than this whole sum of squares. And this sum of squares we call sum of squares total, and this sum of squares we call sum of squares error. So I realize that some of you still may not believe me. So let's calculate this with actual numbers. Okay, so let's see. Here are the predictions from the empty model. And notice that for each thumb, each person, we just predict the same mean for everybody, and that's 62. That's represented by this blue line, right? And so we could actually look at the residuals, square them, see what we get, right? Here I've also put down the group predictions, right? And the group predictions for group 1 is 61, and the group prediction for group 2 is 63. And we could also look at the sum of squares from the group model. So let's get the squared residuals from the empty model. So here I put the predictions, but I'm just going to do a little bit of subtraction to get the residuals. And then I'm also going to make some space for myself to square those residuals. To get the error or the residual, we always want to do data minus model, right? So here's our data here, thumb, minus the model, 62, the empty model, right? And so here we have 64 minus 62 is 2. Let me line them up. 61 minus 62 is -1. 58 minus 62 is -4. 66 minus 62 is 4. 63 minus 62 is 1, and 60 minus 62 is -2. So let's think about this 60 right here. It's that blue dot right here at 60 that's in group 2, right? And so I'm just going to draw a little circle around him, right? And then, so my residual from the empty model looks something like that. And then I'm going to square that residual, right? And so instead of 2, it's -2 squared, which is 4, right? And so that is like that. That is my little 4 right there, right? And imagine that I do that for all of my dots, all 6 dots, right? So here 1 squared is 1, 4 squared is 16, -4 squared is 16, 1 squared is 1, and 2 squared is 4. Right? So you could see my squared residuals from the empty model, and I've put those in blue. Now I'm going to put the squared residuals from the 2-group model, and I'm going to write them over here. Here's my residual, and here I'm also going to make some space for my squared residuals. Right? All right, so to get the residuals, it's the same idea. Data minus model, right? And so my data is thumb, and my model is now over here, right, in the group prediction. So it's 64 minus 61. Let me see if I can line it up well. All right, so I'll put a 3 right there. And then there's 61 minus 61, which is 0. 58 minus 61, which is -3. And then 66 minus 63, which is 3. 63 minus 63 is 0, and 60 minus 63 is -3, right? And then I could square those residuals. And just to illustrate what I'm doing, here we could take this data point, 58 in group 1, and that data point is right here, right? I'm taking the residual which is a -3, and I'm squaring it to get 9, right? And so that's 9, right? And I'm going to do that for all of my data points. So that 0 squared is 0, 3 squared is 9, 3 squared is 9, 0 squared is 0, -3 squared is 9, right? And even without doing the addition, we could see, oh, the sum of all of these is going to be a lot smaller than the sum of all of these, right? And so here we have 18 is the sum of squares for this group. So the sum of squares for this group is 18, right? And the sum of squares for this blue group to over here is also 18. And so it's 18 and 18. And then what I told you was that these two sum of squares would be bigger than these two sum of squares. So let's see if that's actually true. So this first group sum of squares is going to be 16 plus 4 is 20, 21. So the sum of squares here is 21. And then also the sum of squares here is 21, right? And so 21 is bigger than 18. 21 is also bigger than that 18. So when you add them together, 21 and 21 is bigger than 18 and 18, right? And so that's actually true no matter what the means actually are. Whatever the means are for this group, these two groups, that mean is going to minimize that sum of square. And that those minimized sum of squares added together are going to be smaller than these not minimized sum of squares. And that's going to be a real key in why the two-group model has a smaller leftover sum of squares than the empty model does.